Okay. And live stream is starting. Just muted. Here we go. Right, it's 9:30. Hello, everyone. Good to see you. Oh, classic. There's more people coming in right now. Here we go. Now there's a couple of things that I wanted to highlight for today. Number one is we only have one Neuroccino left before the end of the year break. So next week is going to be Eduardo, and then we take a winter break until January the 8th is when we're back. The other thing that I wanted to mention is that Eva has been working very hard to turn us into a podcast. So that is coming, but that also means that we very slightly need to change the way we do Neuroccino, and that is, it'd be great to actually say the title of the paper when you show them. But also when we discuss figures, we might want to describe them a little bit more detailed than just saying here in AU, you can see that they found the results to be significant, okay? Now, this is probably going to be an exercise that we need to keep repeating over the time. But let's see how we're doing with that. Any questions about that part? Nope. Everyone.
We chose papers without figures.
You can choose papers without figures. So you're gonna struggle though, unless you stay historical. At some point, you're gonna run out of papers. Hi, Anna. Great. Okay, now that is clear, that was all the announcements I had for today. So welcome to Neuroccino, our weekly journal club, where we talk about exciting science from last week or before. And today Eva's going to present a paper on fMRI neurofeedback and white matter changes. Eva, if you can share the link in the chat and take it away, please. It's a full house today.
Sorry, I don't have the link prepared.
That's fine. I have it handy here. So if you just want to go ahead and share your screen, I share your link.
Thank you.
Also, Anna, by the way, the rotation, brilliant. Completely nice and de-stressed. The whole thing.
Awesome.
Thank you.
I'm very glad it works out. And I'm super glad Eva is presenting today. Like, look at the rotation thing. So everybody gets to do something. Super cool.
Great idea.
Yeah. So today I wanted to present this paper titled fMRI Neurofeedback in the Motor System Elicits Bidirectional Changes in Activity and in White Matter Structure in the Adult Human Brain by Sampaio Baptista et al. In 2021. And the reason for this is that we had the Donders neurofeedback sessions a couple of weeks ago. We heard a lot about neurofeedback and the effects on function and behavior, but not so much the structure. And when I looked, this was the last paper that I could find that looked into white matter. And as you will see later, also one of the very few. So I think it's an exciting field that is just starting. And yeah. So before I start, I wanted to comment on just what neurofeedback is and how it works with fMRI. You place the participant in an MRI scanner and you analyze their brain activity in real time. And with this analysis, you can generate some kind of, in this case, visual stimuli that tells the participant how their brain activity is. And depending on the task, they can make sure they are modulating it. Yeah. Oh, as well, this has implications for neurorehabilitation or anxiety control. They're looking into this for a lot of clinical fields. So they start off saying that it has not been tested before, whether bidirectional brain activity manipulation can result in white matter changes. So this is the first study looking at this. And they hypothesized that in the same way that optogenetic simulation can lead to cellular changes within 24 hours, we could do the same with fMRI neurofeedback in humans, and this would have implications for clinical tools. And they also look at previous studies, and they find that most previous studies look at functional effects, and only 2 looked at connectivity. One of them was an EEG study, and the other one didn't use tractography, I believe, and also didn't use a bidirectional design. So they established that the previous studies cannot really establish a direct or bidirectional relationship, and they create a new design to overcome these limitations. So they test whether increasing and decreasing sensorimotor activity has differential effects on white matter structure, and during a task of executed movement. So I will explain that with this figure. Yeah, so the way they established their experimental design was they first divided the participants into 2 groups, a neurofeedback and a sham group, each with 10 participants. And the sham group would also receive some sort of feedback, but this would not be informed by their neuronal activity, so it's not real feedback. And these groups would undergo 2 different blocks. In the first block, they would acquire DTI and then do a neurofeedback task of 3 rounds, of each 3 minutes. And after 24 hours, they would acquire DTI of the participants again. Then 2 weeks later, the next block would be performed in the same way. And each of these blocks was for one condition. So they had an association condition and a dissociation condition. In both of these, the participant was asked to move their left hand, so we already expect there will be high activity in the contralateral side, so the right side in this case. But more importantly, they wanted the participants to regulate the ipsilateral side, the left side in this case. In the association condition, they were instructed to rise activity in both sides, whereas the dissociation required to maximize contralateral activity whilst minimizing ipsilateral activity. Yeah, and the way they looked at the different ROIs was using localizer task, where they actually took the ROIs individually for each person, what they used for the hand movements. Yeah, they also did a couple of checks. For instance, they used EMG to make sure that the muscle activity in the left side was actually significantly higher than the right side, because they're not supposed to move their right hand. And this was the same in the sham and the neurofeedback group. And both groups also felt in control of the neurofeedback, even if the sham group was not. Okay, so as for the results, first the functional results, right? Because they need to make sure that the modulation is actually working. So for ipsilateral activity, it was required that it was high in the association condition and lowered in the dissociation condition, and this is exactly what they saw, but only in the back group. Whereas the contralateral activity was supposed to be high for both conditions, and both the sham and the neurofeedback group do. You can see this nicely in the next figure, where we can see that for the neurofeedback group, there is an improvement over time. The association condition, they generate higher activity with each run, whereas in the dissociation condition for the ipsilateral side, they lower their activity. However, the sham group was not able to regulate this ipsilateral activity. And for contralateral, we also see high values across both groups and conditions and runs. They also performed a voxel-wise analysis. And for the neurofeedback group, this cluster in the ipsilateral hand knob shows that there was higher activation in the association than the dissociation condition. And this cluster was not found for the sham group. Right, so now that they had established that the modulation was actually working in the functional sense, they were ready to look into the white matter. So the way they measured integrity and alterations in white matter was using fractional anisotropy, which is a metric that you can derive from DTI scans. And yeah, because they had 4 scans per participant, they decided to compute the difference before and after each neurofeedback session, as well as between conditions. And they did this between participants and for both groups. Now, with these new maps, they performed an analysis called track-based spatial statistics in order to see which areas were changing due to the neurofeedback, basically. And this approach consists of computing a representative skeleton of the white matter of each participant and then comparing between these skeletons. And they found a cluster in the corpus callosum indicating higher fractional anisotropy, so higher intensity in the association condition and lower in the dissociation condition. And you can see this cluster over here in the ipsilateral side of the corpus callosum. And they also took this cluster and performed tractography from it. So yeah, they saw that it linked sensorimotor and parietal cortices. So yeah, that's it for the results and their discussion. Well, they conclude that indeed bidirectional activity showed bidirectional effects, also quite quick effects in just 24 hours, and localized to the hand knob area in a functional sense and to the ipsilateral side of the corpus callosum in the structural sense. They think that this could be due to myelination, as similar timelines have been shown to, yeah, that you're able to produce this myelination, but of course there could be many other structural properties that could be changing and they could affect the fractional anisotropy measure, so this is not entirely clear. They also acknowledge some fMRI limitations, and for the corpus callosum results, they just deduced that the modulation must be occurring via this tract, but it could be also other tracts because they mentioned that since the corpus callosum is a coherent fiber bundle, it's more likely that small changes are found here. They were also surprised to see modulation in only 1 session, as you already saw in the training blocks. They were already improving, and this is faster than seen in other studies. Yeah, regarding the contralateral activity, even if the participants were instructed to maximize it as much as possible, they were not really able to do this, and they think it's because of a ceiling effect where you're already moving your left hand and it's harder to modulate on top of the high activity that is already expected. And another very important thing in neurofeedback is the variability in responses. Some people are classified as responders and non-responders. And here, very briefly, they tried to look into some baseline measures of the integrity of different tracts, and their conclusion is that highly structurally connected motor networks might be harder to modulate. but they have a relatively small sample size to look into this variability. And finally, well, the clinical impact of this one, since it was executed movement, it would be neurorehabilitation and also interventions in participants after stroke. And because of this variability and how flexible this approach is, we could tailor these interventions to the individual. And finally, they just acknowledge some further limitations, such as carryover effects, because the two blocks were separated only by 2 weeks. Also that they did not look into gray matter volume changes and not able to assess transfer effects. And of course, the small sample size. So yeah, this is the paper. I hope you liked it. And overall, I was quite surprised to see measurable effects in 24 hours, but then they explained that this plasticity can be this quick. And for me, it would have also been interesting to perhaps compare after the 2 weeks, like how long does this structural change last? Does it stick as much as functional effects, as much as behavioral effects? What is the decay rate of these things? But they probably did not have enough to make this kind of analysis. But there is a lot to look into in this field, and yeah, I hope you got excited as well.
Thank you so much. Exciting paper. There's a lot of questions coming up and a thread in the chat, which is more about the annotations and how lovely it looks.
Oh.
I guess people would be interested in knowing which tool you used for that as well.
Oh, it's Good Notes on the iPad.
Here you go. I think Chris was the first with a hand up.
Well, thank you for presenting this paper. It's really exciting. I was a little bit skeptical about the changes, but because it's a movement task, actually, when you're training a specific movement, you can see like significant changes from one day to the other. So I guess that makes sense. But as you said, I also I was about to mention that it would be interesting to see if the changes last, how long they last. But how do you think that would work with tasks that are not motor? Because as I said, you can feel the changes in a motor task. If you're training, I don't know, if you're learning an instrument, or if you're learning to do something with your hands, you will see a change from one day to the other. But if you're training for something that is a little bit more complex, maybe, or more let's say intellectual, like you don't use your movements, do you think that would work the same way? Do you think we would see longer changes to take place, but also would they last longer? I mean, I guess it's just one preliminary study in this field, but yeah, do you think that would be we would see big differences with different tasks, and if it would even be possible? Because you need to be in an MRI machine with very big constraints.
Yeah, good question. Yeah, they are also doing neurofeedback, for instance, for anxiety disorders, and you train perhaps changing between different functional networks or the strength of different networks. So measure connectivity in these, as well as functional and structural connectivity. How long it would last, or if it would last longer than the functional effects, is that a question? I thought about this as for instance, a bodybuilder might might stop training, but the sort of scaffolding stays there for longer, and maybe they're able to pick back up strength faster. So I also would be curious to see if the structural and the functional effects decay in the same way, or if they don't. There would be ways to measure the anxiety distance, but this might be less exact than measuring how well you can move, or so you also introduce more possible
because
error.
also when you think about it, like if we could measure changes in the white matter that quickly, if we were like every day we do stuff, so every day our white matter should change in a measurable way in an MRI, but I'm a little bit surprised by that. So like
I was surprised as well.
Motion, I can believe that, but for other things I'm not sure.
I would say with other things you would probably need a longer time frame, like weeks and several sessions. But I know that there are some studies looking into behavioral effects after only one neurofeedback session for 15 minutes. So they're seeing behavioral effects, and I don't know really about the structural. I was also really taken back, like, okay, in just 24 hours you can see this? Is this really measuring what we think it is? But I don't know.
Yeah, that's the question. Yeah, thank you.
Well, part of these authors were also on the original study looking at the plasticity when people learn to juggle, and they were able to show the changes there. So it's a continuous thing. Eduardo.
Thank you for the presentation. My question is more about the mechanism they mentioned for these changes. So you told us it was they thought about changes in myelinization. Now maybe my knowledge is not up to date, but I think Beaulieu and Allen already established a while ago that actually diffusion-weighted signal in MRI scans is not mostly due to myelin sheets, but rather to the structure of the cell membrane of the axons, for example. So I was wondering if they mentioned also other possible explanation for these effects. And
I think they list a couple of possible explanations. They say axon density and caliber, astrocyte morphology, cell swelling, or membrane fluidity could also be altered by this neuronal activity, and then underlie the effects. So I think they're not really also trying to look at the how, perhaps, or like what really is going on in the at that level. But obviously it's important to.
I was curious because they mentioned like possible rehabilitation applications, and probably there's something you might need to know to build up something in that direction. Okay, thank you.
Very much. Misha's getting ready, adjusting his camera. Go, your question.
Thank you, Steph. So in 2011, there was a study showing that in 24 hours, you can have a change in the white matter. So we're using this Need for Speed game, having participants doing always the same circuits, and other participants doing a different circuits every time. And they compared before, after DTI, and found in just 2 hours, they found change in the mean diffusivity in the hippocampus. And then they did the same task with mice, obviously not Need for Speed. There was like the kind of swimming pool with like a platform paradigm, always the same place for the platform or a different place. And so mice learn where is the platform. And they found that this change in the hippocampus was linked to an increase of the size of the astrocytes. And in mice, because they did also the diffusion, they found change in the white matter in the corpus callosum. And that was an increase of the size of the oligodendrocyte. Although in mice, it was in 2 weeks. So this is a higher level cognitive function. That's a question of Chris that has been shown to be related with very fast change in the white matter. And this is really exciting because that means like you can change your connectome very quickly and measure it with MRI. So maybe in the future we should think about doing similar experiments, or at least integrating that in our way of reasoning of inter-individual viability and recovery after a brain injury.
Yeah, thank you.
But then for recovery after brain injury, there's also this misconception that the white matter regrows, right? So if you have a stroke, the hole that is left by the lesion does not get refilled with white matter due to plasticity. And likewise, if you have FA changes, for example, where FA increases, that's not necessarily a sign of plasticity, but just reduced crossing after a lesion. So in the context of a pathological brain, what we consider as plasticity depends very much on the methodological details that we need to be aware of.
There's a lot of, well, by plasticity, I mean like bypass, increasing connection with other areas.
I know, plasticity is used in many different terms.
Make it clear, you're not going to regrow a 20 centimeter track.
Yeah.
Just out of plasticity, it's not going to happen. But you can have some axonal proteins that can compensate a little.
And functional plasticity and all that, but that's something to be aware of. Great. In that case, thank you very much for that exciting paper. We have one more Neuroccino left next week. Eduardo is presenting. For those of you who have access to the rota sheet, you can already see the paper that he chose. And other than that, I wish you an exciting week in science and see you next week. Bye.